Hey there guys, welcome to Unit 6. In our first set of notes, we're going to go over some basic things you should know about chemical reactions. So once we go over the introduction, we'll get into types, and throughout this entire thing, we'll be talking about balancing. So let's get started with chemical reactions. First of all, how do you know that you've seen a chemical reaction? How can you identify a chemical reaction? Well, there has to be some kind of rearrangement of atoms. So the reactants have to be completely different from the products. So not a phase change, but an actual chemical change. So the identity will be different in the reactant versus the product. But how can you tell that just macroscopically or with your eyes? You're looking for gases and color changes, bubbling, things like that. Careful you don't mix that up with like boiling, just producing vapor. But yeah, you're usually looking for something that has a completely different characteristic than when it started. Let's talk about the energy in a chemical reaction. In order to break bonds, you have to input energy. Remember, atoms formed bonds in order to achieve a stable electron configuration. So messing that up is going to require some energy. On the flip side, when you form bonds, you are allowing those atoms, their electrons, to become more stable, and so that would produce a release of energy. So sometimes chemical reactions as a whole will add more energy than they release, and sometimes the other way around. But you gotta be careful because overall you want to follow the law of conservation of energy. So just to recap a little bit of vocabulary about releasing or absorbing energy. An exothermic, exo like EX like exit, will release energy. And what this basically means is that they're releasing more energy as they form the products than they needed to break the bonds in the first place. An endothermic, EN like enter, would absorb energy, and it would be exactly the opposite. So if this isn't even, then how does this follow the law of conservation of energy? Well, remember, there's the surroundings. So if you touch a beaker and it feels hot, the chemical reaction inside must be producing energy, and that energy is being emitted to the surroundings, like your hand. On the flip side, if you touch a beaker and it feels cold, that would indicate that it's pulling energy in from your hand, or absorbing energy. So we've got to consider the surroundings, and then it'll follow the law of conservation of energy. All right, as far as chemical equations go, we want to make sure that we consider the reactants individually, what formulas they would have, and then the products, and write those accordingly. So let's look at a word problem, which we're going to see a lot in this unit. If we have hydrogen gas, would that exist as hydrogen or as H2? How can you tell? Well, there are exactly 7 elements that are diatomic, and hydrogen is one of them. And then it's going to react with oxygen gas. Was oxygen on that list too? Yes, it was. So I know that I have H2 reacting with O2 to form water, or H2O. Notice that I represented the words to form with the arrow. My reactants are turning into products. There's one last problem with this reaction, the way I have it written. Can 2 hydrogen atoms and 2 oxygen atoms form a compound that only has 1 oxygen atom with the 2 hydrogen atoms? The hydrogens are fine, but can that oxygen atom really just disappear? Of course not. There's also the law of conservation of matter. So in order to fix this kind of offset 2 versus 1 issue with the oxygen, we're going to need to do what's called balancing the equation. So that means I'm going to need 2 water molecules. Well, now that makes me have 4 hydrogen atoms on the product side. So now I got to revisit the reactant side and make there be 2 hydrogen molecules for a total of 4 hydrogen atoms. Now there's 4 hydrogens on each side and 2 oxygens on each side, which we would say is balanced. So that is our goal here, is to be able to write balanced equations. So you start off by identifying formulas, then you balance it with what we call coefficients. All right, so let's kind of break down what a chemical equation is going to show us. The formula of the reactants. You've got to know whether they're diatomic or not. You've got to be able to go from name to formula sometimes to be able to write your formulas of the reactants. You've also then got to predict your products. So we're going to go over some types of reactions, and you're going to be able to predict what products will form and give them the correct subscripts there. Then we're going to add the coefficients, and we'll talk a lot later about how those coefficients actually give you what's called a mole ratio. That's going to tell you basically relative amounts of how much of each substance is involved in the reaction. So these are all important parts of a chemical equation. This is a typical format. This is the one we were just doing, where the hydrogen gas, oxygen gas formed water, and we balanced it. The reactants will always go on the left-hand side, and the products will always go on the right-hand side of the arrow. A lot of times in word problems it will say to form, but you could also read this as yields. Hydrogen and oxygen yield water. So there's kind of our setup for our chemical equation. The other thing that you're going to see in chemical equations is after the formula. So for example, if I had hydrogen gas, I just said comes as a gas, we can put the G. And then it reacted with oxygen gas. So I can put the phases kind of after the formula. So if you see an S, that would mean solid, an L would be liquid, and they do usually make it cursive so that you can tell it's an L and not a 1. G for gas, and then AQ is one that you're going to actually see a lot. What that means is that it's been dissolved in water. So picture taking table salt and putting it in water and making salt water. That would be aqueous or aqueous table salt. You can also use arrows instead of the letters. And in that case, you don't need the parentheses. I like the letters better myself, but either one is fine. Either way, it goes directly after the formula, and you're indicating what phase the substance exists as. So you can tell by the arrows it's a gas, and by the L it's a liquid. All right, so let's see if we really understand what aqueous means. It's one of the harder phases, right? What do you think the difference between aqueous table salt versus liquid table salt would be? Well, aqueous table salt would just literally be salt dissolved in water, where to get liquid sodium chloride, you would have to take table salt and literally melt it. So like reach its melting point and have it turn from the solid phase into the liquid phase. No water involved. So if that happened, you'd have pure melted salt in a liquid form, whereas just dissolving it in water, getting it to go into the water, would be the aqueous form. So they are very different phases. All right, let's try writing a chemical reaction, including the phases. We're going to react iron with oxygen to form iron 3 oxide, also known as rust. So let's start with our reactants. What will be the formula for iron? The symbol is Fe, but you have to think, is it diatomic? And iron is not on the list, so it's going to be all by itself. How about oxygen? Is oxygen diatomic? Yes, it was. So we've got our O2. To form means I'm at the spot where I'm going to draw the arrow. And then what am I forming? Iron 3 oxide. So iron 3, that Roman numeral 3, did it tell me the charge or did it tell me the subscript or something else? It told you the charge. So it's going to be +3 is what that means. And then oxygen, we should know its charge because it's in column 16, is going to be -2. Now, how do you neutralize the charges? Remember our crisscross. So the formula for iron is Fe2O3. Now, is this balanced? I have 1 iron atom becoming 2, and I have 2 oxygen atoms becoming 3. That's impossible, right? So how am I going to fix that? Well, I would recommend starting with your odd numbers. If something is by itself, I would save it for last because it's the easiest to fix later. So I'm going to start with my oxygen. If I have 2 on the left and 3 on the right, what would I have to bring them both up to in order to make them even? It's kind of like lowest common denominator type of thing. So we've got 3 and 2, we need to bring them up to 6. So that means I'm going to need 2 of the iron oxide compounds, and I'm going to need 3 of the oxygen molecules. That's going to make me have 6 oxygens on the left and 6 oxygens on the right. Since the iron comes in pairs for 2 molecules, now I have 4 irons, which I can fix really easily over here by just adding a 4 instead in front of that solo iron. So this is my balanced formula. But remember, we wanted to include phases this time. Iron is a metal, and most metals are solid at room temperature. Oxygen comes as a gas at room temperature. So we'll use our G. And then rust, you've probably seen rust before, right? That red powder, solid. So we can use our S's and our G's right after the chemical formula to indicate the phases. So we were able to write our balanced formula with phases, just thinking through it one step at a time. All right, so now that we've talked about both coefficients and subscripts, let's make sure we know the difference. Coefficients were the things that came in front. That's what I added to balance the equation. Whereas a subscript, we've been using already. That's what you get from crisscrossing the charges. That only applies to the atom it's after. So this 2 only applies to the hydrogen, and this 4 only applies to the oxygen. Remember, we've also used subscripts with parentheses before too, and that would apply to everything just inside the parentheses. Then you have coefficients, and that's going to apply to everything it's in front of. Notice the size of the coefficient, same size as the letters, whereas the subscript is smaller and sub below the script. So 2 completely different types of numbers here. Coefficient versus subscript. Coefficients are used to balance equations. So let's just do a quick review on what you're doing when you balance the equations. First thing you want to do is make sure you have correct formulas to work with. Then you're not going to change those as you balance the equation. So make sure you get your formulas first and then move into balancing. Write your reactants on the left, your products on the right, and then you want to count how many atoms of each there are and see if it matches. If it doesn't match, then you're going to need to introduce the coefficients. And there's no easy, clear-cut way to do this. It's kind of like a puzzle that you have to solve. How can I get these atoms to balance on each side? And when you add a coefficient, you're going to affect all the atoms. So that may cause you to then have to rebalance some other atoms that you already thought you fixed. At the end, you always want to check to make sure that you didn't throw off the other atoms. That can happen where you think you fixed the oxygen, then you add a subscript and you mess up the oxygen count. You want to make sure that you double count at the end. Another problem that can happen is if you get so tied up into making sure that they're the same on both sides, sometimes you can miss the lowest common denominator. So if at the end, the coefficients can reduce, you should reduce them. So for example, 2 to 4 to 2 should reduce to 1 to 2 to 1. So just like when you crisscrossed, even with the coefficients, you want to make sure that you reduce them at the end. So this should get you balanced equations. The biggest mistake people make with balancing equations is confusing the subscripts with the coefficients. Subscripts are used to balance charges. Once you identify the substance itself, you do not change the subscripts. If you changed H2O into H2O2, you would be making water turn into hydrogen peroxide. You wouldn't want to do that just to balance the equation. What you would be wanting to do is add a coefficient instead to show 2 water molecules, not changing that into a completely different substance, right? So you first handle your subscripts, identify your formulas, and then you move into the coefficients. So never ever change the subscripts as a function of balancing. All right, let's get into our types of reactions. There are 5 main ones that we're going to go over today. The first is called synthesis or combination. You may recognize synthesis from like photosynthesis, making. So this is going to be combining, making a compound out of 2, basically like 2 reactants combined to form 1 product. So, but the catch is these could be diatomic or just atoms. Decomposition is going to be exactly the other way around, taking a compound and breaking it down into its parts. Single replacement is going to be taking a compound and then 1 atom swaps out another, whereas double replacement is 2 compounds that kind of swap cation and anion partners. And then our last one, combustion, it just means that we're dealing with oxygen and getting little, you might have heard combustion meaning explosions. So they don't have to be big explosions, but we're going to be using oxygen up because there is some type of explosion there. We're going to look at what's required for that. So basically it needs oxygen. So let's go through this a little bit more slowly, starting with our synthesis or combination reaction. So in this case, you have 2 reactants combining to form 1 product. So an example of this would be potassium reacting with chlorine in order to form potassium chloride. Notice that there's a 2 on the chlorine on the reactant side, but not on the product side. Chlorine is diatomic, so when it's alone, it will have a 2. Potassium is not diatomic, so no 2 there, right? Potassium has a +1 charge. Chlorine has a -1 charge. So we don't need any subscripts to balance the formula here. The charges are balanced. What the problem is that means that I have 1 chlorine versus 2. So how do you fix that without adding subscripts? You use coefficients. So that's where the 2's come in front of that. So anything that has 2 reactants, 1 product, would be classified as our synthesis reaction. Let's work through a couple. So let's start with calcium and chlorine. Calcium, not being diatomic, does not have the subscript, whereas chlorine, being diatomic, does have the subscript. Now I want to combine them. So I'm going to make a calcium chloride. Whenever you combine 2 atoms, you want to make sure that you have the charges balanced, or I should say combine 2 ions, right? Calcium, being in the second column, has a +2 charge, and chlorine, being a halogen, has a -1 charge. Is that balanced? What would be the compound that we would make in order to have that balanced equation? I'm sorry, the balanced charges. We would have CaCl2, the +2 charge crisscrossing. So 1 calcium, 2 calciums, 2 chlorides, 2 chlorides. Are we balanced? We got lucky this time. Yes, that is balanced. If it's the same, you don't need to add any coefficients. So that would just be our calcium reacting with the chlorine in order to form the calcium chloride. And if you know the phases, go ahead and include them. Metals come as solids usually, and we have our chlorine, which will come as a gas. All right, let's look at one that's not written out as what the symbols are, so more of a word problem. So sodium, the symbol for which is Na. Then the question is it diatomic? So when it gives you the word problem, you have to figure that part out for yourself. So sodium is not one of our 7 diatomics, so I won't use a subscript of 2. Then I'm going to react that with oxygen. Is oxygen one of your diatomics? Yes, it is. So we will have a subscript of 2. Then I want to form the compound where I put sodium and oxygen together, NaO. And whenever you form a compound, you have to check the charges. So sodium, being an alkali metal, has a +1 charge, whereas oxygen in column 16 has a -2 charge. So how could I balance those charges? What would be the formula for sodium oxide? That would be Na2O. Crisscross the charge of the -2 onto the sodium. So let's see what we've got now. 1 sodium versus 2, and 2 oxygens versus 1. It's a problem for both atoms, right? Remember, you can fix something by itself super easy, so we'll leave that for last and start with our oxygen. If I have 2 oxygens here and 1 there, I must need 2 oxygens on the right. Can I fix that by making this Na2O2? No, because that would unbalance my molecule's charges. It wouldn't exist. Na2O2 just does not exist. So what's the only other way that I can get 2 oxygens on the right? A coefficient. But that's also going to change my sodium count. So if I have 2 sodiums per molecule with 2 molecules, I need 4 sodiums. So 4 Na plus O2 yields 2 Na2O. And we have our balanced formulas. Or balanced equations. And yes, the metal is a solid and oxygen comes as a gas. Right, so combination, you first figure out the formulas for your reactants, you neutralize your charges when you make the product, and then you add your coefficients at the end. Alrighty, so you do need to be able to work from the word equations. Let's look at our next reaction, decomposition reactions. So decomposition is essentially the opposite of synthesis. So we're going to take 1 reactant and break it down into 2 products. So synthesis was 2 things becoming 1, decomposition is 1 thing becoming 2. So it's exactly the opposite. So you're going to take your compound and you're going to break it apart into the 2 atoms. So H2O would break down into H and O. Then for the products, you have to determine, is it diatomic or not, in which case here, but they both are, and then you go back and balance with coefficients. So anytime you have one thing breaking down into two, it is called a decomposition reaction. Let's try a couple. So let's look at our magnesium oxide first. The formula, Mg plus 2 and O minus 2, notice does not have any subscripts. But when I break it down into magnesium and oxygen, you have to determine if the products need subscripts. And to do that, you just need to know if they're diatomic or not. Is magnesium diatomic? No. Is oxygen diatomic? Yes. So the oxygen will need a subscript. But that means now I have one oxygen on the left and two on the right. So that's a problem. How do we fix this imbalance? Should we come back and add a 2 to the reactant? The formula for magnesium is MgO, period, end of story. So the only other thing I can do is add a coefficient. But that's also going to change my magnesium count. And so I'm going to add a 2 in front of the magnesium as well. So it's going to now make me have 2 magnesiums on both sides and 2 oxygens on both sides. So, and you can see some of the common phases again, the metal being a solid and the oxygen being a gas. So if it gives you the words, you have to come up with the formula. So this is very similar to what we did in the nomenclature unit. Silver is Ag and bromine is Br. But you have to consider the charges. From Things to Know and Love Part 3, you should know that silver is always a +1 charge, and then bromine being a halogen would have a -1 charge. So +1 and -1 do cancel, and so that is the correct formula for silver bromide. Now I want to break this down and separate the silver and the bromine. So I'm going to have Ag and Br. Now are either one of these diatomic? Our bromine is. So now that unbalances my bromines. I'll fix that with a coefficient, which will mess with my silver. So I've got to fix that over here as well. So it kind of all comes from the subscripts. You got to switch gears and balance that with the coefficients. So there we go. And again, we have our solid metal and our bromine is a gas. So that's our decomposition. Come up with the, if it's words, come up with the balanced formula. And then when you break it down, you consider diatomic or not, and then you need to balance. All right. So next reaction is called a single replacement reaction. So in this reaction, you're going to have an atom and a compound as your reactant. That atom is going to replace part of the molecule. That means that molecule part that's replaced then gets kicked off by itself, and there will be a new compound formed. So the idea usually is that we're going to need this cation to replace a cation, and then that means the anion will still come second. There is a catch. Here's an example where the magnesium would replace the silver. So that's now going to make magnesium nitrate. But you're going to still write the magnesium first. When you do that, you have to consider the charges. So silver only had a +1, but magnesium would have a +2. So that's where this 2 comes from. That unbalances everything, and so that's when your coefficients come in. But it is possible to have no reaction. So there is a order hierarchy, per se, of reactivity. And in order to actually cause this replacement, the new guy has to be better. So in this case, I could tell that magnesium is not better or more reactive than lithium, hence the no reaction. So how can you tell what's better? How can you tell what's more reactive? So that's something called the activity series. And this is on your cover sheet, giving you the order. Lithium being at the top will replace everything, meaning nothing can replace lithium. Silver being on the bottom can't replace anything, and everything can replace it. If we're looking in the middle, let's compare like sodium versus zinc. Sodium can replace zinc, but zinc cannot replace sodium. So in order to be the replacer, it has to be higher. The anion has to be upgrading. All right, so let's look at a couple here to compare the increasing activity. So let's look at calcium trying to react with the magnesium oxide. Will calcium be able to replace the magnesium? Here's calcium, here's magnesium. Is calcium above the magnesium? Yes. And so if it's above, then yes, it can replace it. And so then you'll get your calcium oxide and your magnesium. The one thing that you want to be careful with is when you make your new compound, just like with the synthesis reaction, that you balance the charges. So calcium's +2, oxygen's -2, and so that's how this works out with no subscripts. So we only have to check the activity series with single replacement reactions, but you always have to check it with single replacement reactions. All right, let's try calcium with silver. So looking at your activity series, will calcium replace silver? Is calcium higher than silver? Well, you may remember silver's all the way at the bottom, so anything will replace silver. So yes, I'm going to be able to replace the calcium with the silver. I'm sorry, I'm going to replace the silver with the calcium. So calcium's going to now bond with the chloride. The chloride upgraded to a better, more reactive element. But then I have to consider the charges. Calcium, being in the second column, has a +2 charge, where chlorine only has a -1 charge. So that means I'm going to need 2 chlorines, crisscross. By the way, you always want to make sure the cation comes first in any ionic compound. So you want to make sure you're writing calcium chloride, not the other way around. So then what happens to the silver? Well, it just gets booted out. Goodbye, silver. Go away. So we got our calcium chloride and our silver. Now we got to look back, now that we've got all of our formulas, is it balanced? And it's not, because we've added a subscript. So does that mean I can just come over here and add a subscript? Well, no, because this is +1 -1. So the formula for silver chloride is AgCl. So we've got to add a coefficient instead to make there be 2 chlorines. Well, that's also going to affect the silver. So I've got to adjust our product on the silver as well. So there we've got our balanced reaction. Calcium replacing the silver to make the calcium chloride, kicking out the silver. All right, let's look at sodium reacting with potassium chloride. So sodium symbol is Na. Whenever I write an element, I've just got to think, is it diatomic? And it's not. And then we're going to write our potassium chloride, KCl. Whenever you go name a formula, you've got to think about the charges. So this would be +1 -1, balanced. Now I've got to check, since this is single replacement, does the sodium replace the potassium? So for that to work, the sodium would have to be higher than the potassium. Is that the case? It's the other way around. The potassium is higher than the sodium. So chlorine's already with the better element. So it's going to say, no, go away, sodium. And so we would write no reaction. If the element trying to do the replacing is lower, it won't work. Nothing will happen. And so we'll call that no reaction. And you would just write no reaction. All right, so the next reaction we're going to look at is double replacement reaction, but I think it's about time for a quick break, so we will be right back. All right, guys, welcome back. We've got 2 more types of reactions to get through. Double replacement reactions will involve 2 compounds. They're both going to be ionic compounds, and the idea is that the cation and anion pairing has to swap. So it has to be an exchange, a swapping, between the 2 different ions in the compound. So here's kind of a color-coded example. Right here we have cation 1 and anion 1, and here we have cation 2 and anion 2. So right now, cation 1 is paired with anion 2, but in our product, we want cation 1 and anion 2 to pair up, X and Y, and then we want anion 1 and cation 2 to pair up, which is how we get Ba here. So this kind of reminds me of FOIL in math class, actually. You're kind of swapping the beginning cation and ending anion together, and then your ending anion and this cation coming together. So we're making new matchups. All right, so if we look at this, you can see sodium was with cyanide, but now we want to match sodium with sulfate. So we get a sodium sulfate. Here we had cyanide with sodium, but now we want to match the cyanide with the hydrogen. So you get this hydrocyanic acid. Notice that no matter what, at the end though, cation, anion, cation, anion. Cation always comes first. So you've got to be careful with this inside set, because if you're reading from left to right, you're going to come across the anion, then the cation. But when you write it as a product, you have to write the cation first. So you want to be careful that you're adjusting cation first. The other thing you want to be careful of is that you're coming up with your own subscripts for these new pairs. Just because there's a 2 on the H with this sulfuric acid doesn't mean that there would be a 2 on the H once it's bonded to cyanide. Cyanide has a -1 charge and sulfate has a -2 charge. So we want to make sure that we are making neutral compounds first. Once you do that, you can fix all of the unbalanced problems with your coefficients. So anything that has 2 compounds, you can tell automatically would be a double replacement. It's the only one that we've come across that has 2 compounds. And then the idea is that we're swapping pairs of cations to anions. So let's try one. So we got our calcium hydroxide and our silver phosphate. So I'm going to take my calcium from the first atom, my first cation, and pair that up with my anion from the second atom. I'm going to pair calcium with phosphate. So I'm going to write Ca and PO4. What would be the correct formula for calcium phosphate? Since calcium's in the second group, it would have a +2 charge. And then you should know from Things to Know and Love, the phosphate has a charge of -3. So in order to balance these charges, this would need to be CO3. I'm going to put PO4 in parentheses with a 2 on the outside. So the correct formula for calcium phosphate only comes one way. Ca3, PO4, 2. Notice this 3 and 2 did not exist in the reactants. That was created by the charges in the new compounds. Now what's the next one? Let me use a different color here. We're going to take our silver and our hydroxide, and we're going to pair those guys. When I write the product though, I'm going to use the cation first. So the first thing I'm going to write down is the silver. Then I'm going to write down the hydroxide. Once I make a silver hydroxide, I've got to consider the formulas, the charges to make the formula for that as well. So silver from Things to Know and Love Part 3 has a +1 charge. Hydroxide from Part 2 has a -1 charge. So +1 and -1 cancel out. So I actually don't need any subscripts for the silver hydroxide. Notice how they had them and now they don't. So it all has to do with what it's attached to in terms of subscripts. All right, let me clean this up a little bit. Now, is this balanced? Absolutely not. Not even a little bit, right? We've got 2 hydroxides, 1 hydroxide, 2 phosphates, 1 phosphate, 3 silvers, 1 silver, and 3 calciums, 1 calcium. Not one part of this is balanced. So I would start with my odd things. Like for example, if I know that I need 3 calciums, I'm going to need 3 calciums over here. That's going to create 2 hydroxides per molecule, 3 molecules, a total of 6 hydroxides. So I'm going to put the 6 in front of the silver hydroxide. Now that makes me have 6 silvers. So where's my silver? Over here. We had 3 silvers. If we need 6, I'm going to need a 2 in front of that. Now that 2 would apply to the phosphate as well. So let's go over here. Well, it already came as a pair of 2. So wherever you decide to start, if you just keep following that, you're going to be able to find your coefficients. But you always, always, always want to check at the end and make sure you actually fixed everything and didn't accidentally undo something you thought you fixed. So let's check. I have 3 calciums, 3 calciums, 6 total hydroxides, 6 hydroxides, 6 total silvers, 6 silvers, and 2 phosphates to 2 phosphates. So when you're doing a double replacement reaction, because the polyatomic ions kind of stay together, you can treat them as a unit as you balance the equation as well, which can speed things up. But if we counted this out as separate oxygens, hydrogens, and phosphoruses, that would also balance. So we do have finally a balanced equation. Uh-oh. Red does not want to erase so much. Give me 1 second. Moving my whole board. All right, note to self, do not use red. Sorry, guys. All right, let's try one with words. So now I have to go from from name to formula, balance those charges, then do the cation anion matchup, then I have to balance it. So this is gonna be one of the longest problems we've done so far. Let's get started. Sodium nitrate. So sodium is gonna be the Na, and nitrate would be NO3. What's the correct formula for sodium nitrate? +1 and -1, so I don't need any more subscripts. That's it. It's going to react with, so the plus sign, ammonium sulfite. So ammonium is NH4. Sulfite would have one less oxygen than sulfate, so it's going to be SO3. Now, do we need any additional subscripts? We do. Ammonium only has a +1, whereas sulfate would have a -2. So there's actually 2 ammoniums. Now it's time for the crisscross. So what are we going to pair? I want to take my beginning cation and my ending anion and put those 2 things together. Sodium and sulfite. Na and SO3. Now, do I need any more subscripts to make the formula for sodium sulfite? And I do. Sodium only has a +1, but sulfite has a -2. So this is going to need to be Na2SO3. What else am I going to pair? I've got my nitrate and my ammonia. So I'm going to make NH4 match up with NO3. Ammonia is +1, nitrate's -1. So do you need any more subscripts? No. That's going to match up 1 to 1. So it's a big formula, but that's just ammonium nitrate. So now that we've got our formulas, we want to make sure that we avoid changing the subscripts. These are the way that the molecules exist, period, end of story. So now we just need to see if it's balanced. Is this balanced? There's 1 sodium here and 2 there, which would be a problem. 2 ammoniums to 1 ammonium, also a problem. So what would I want to do in order to balance this? Well, it seems like I need 2 sodiums, so let's put a 2 in front of the sodium, which is going to make it so that there's 2 nitrates. So where's my nitrate? Over here. So I'm going to put a 2 in front of that as well. Sorry, that's a little messy. Actually, let me just rewrite that real quick. So we're going to say +2 NH4NO3. And so that now has 2 ammoniums. So if we go over to find our ammonium, it already has 2. So we want to check the one thing we haven't talked about yet, 1 sulfite to 1 sulfite. So we're balanced with putting a 2 in front of the sodium nitrate and in front of the ammonium nitrate. That's going to fix our problems. So that's our final equation here. Just to recap, because this was a big problem. We take our words and turn them into a formula. So sodium nitrate was just NaNO3, and ammonium sulfate was NH4 from the 2- charge, and sulfite with 1 less oxygen. Then we're going to pair the sodium with the sulfite, but that becomes Na2SO3 from the sulfite charge. And then we're going to pair the ammonium and the nitrate, making sure to write ammonium first and then the nitrate. That's +1 -1, so the formula is good, but to balance it, we needed 2's in front of 2 of the molecules. So that's going to give us finally our total equation, balanced and all. Okay, so we need to be able to go from word to formula, predict the products, and balance. One last reaction, combustion reactions. So these are the fun ones. This is where we're reacting it with oxygen. You're getting some type of little explosion. It's producing a lot of heat and light. So what do we need in order to have some kind of fire, some kind of explosion? Fire needs oxygen. So basically, in order to classify a reaction as combustion, you need to have oxygen on the reactant side. It doesn't count as combustion if oxygen is on the product side, and it doesn't count as combustion if it's just a compound that happens to have an oxygen atom. It has to actually be diatomic oxygen on the reactant side. Anytime you have that, it's going to be considered combustion. So any type of O2 on the reactant side is considered combustion. there is a special kind of combustion that you need to know about, and these are the ones that you're going to be able to need to write from words. This is called hydrocarbon combustion. So hydro actually means hydrogen, and carbon, of course, would represent the carbon. But usually when you write the formula, carbon comes first, right? So if you see C something, H something, anything that's just made of C and H, that's going to be a hydrocarbon. Whenever we have combustion, or reacting with O2, the products will always be the same, and you do need to know what they are: carbon dioxide and water. Then the balancing will come from what the subscripts are on the hydrocarbon. A trick I would recommend is to do the C first, then the H, then the O. It's going to lead to a lot less trial and error just based on where things are. So C first, then H, then O. Just save you a little time. Of course, you can get there no matter which way you approach it eventually. Alrighty. So let's look at our last set here. Now, combustion is anything that has oxygen, but without knowing it's hydrocarbon combustion, that's not really going to help me solve this problem. So here's a trick. What other type of reaction does this look like? Magnesium reacting with oxygen. What was it where I had two reactants forming one thing? That's also called synthesis. So yes, a chemical equation can fit more than one type. So this is not only combustion, but also synthesis, which is going to allow me to predict the products where magnesium combines with oxygen. Remember, whenever you make a new compound, you have to balance the charges. +2 for magnesium and -2 for oxygen will balance. And so we just need to worry about balancing the overall equation. So can I put a subscript here? That's the big no-no, right? That would unbalance the charges. So I'm going to use a coefficient instead, which will mean now there's 2 magnesiums. So I need a coefficient on the magnesium on the reactant side as well. So if it's not hydrocarbon, you have to figure out what other type of equation it is. Usually synthesis and combustion are pretty hand in hand. That comes up a lot. So let's look at a word problem that is hydrocarbon combustion. This is all you get, is what is the hydrocarbon. Anything that's burning would have fire, and so fire would need oxygen. So that means this is combustion. C2H6 reacts with oxygen. How am I supposed to figure out what the products are? Well, you have to know that hydrocarbon combustion always produces carbon dioxide and water. So we're going to write down CO2 and H2O. Those will always be your products from your hydrocarbon combustion. So basically, I give you the hydrocarbon and you have to know the rest. Now, is it balanced? I don't think so. So what were we going to balance first? The carbons. So if I have 2 carbons on the left, that means I'm going to need 2 carbon dioxides. Next, we're going to look at the hydrogens. If I have 6 hydrogens, how many waters would I need? Keeping in mind that there's 2 hydrogens per water. I would need 3 waters. So that's going to go ahead and give you coefficients to work with for both the carbon dioxide and the water. Now the question is, how many oxygens does that make? So if I have 2 per carbon dioxide and I have 2 carbon dioxides, I have 4, oops, it's a little sideways. I have 4 oxygens here. And then if I have 1 oxygen per water and 3 waters, that's going to give me 3 oxygens from the water. And together this would be 7. So I need 7 oxygens here. They come in pairs. So it's kind of like I need 3.5. But wait a minute. Have you ever had a half coefficient? It's not a thing. So what I would do at this point, instead of having to play trial and error with everything, how did we make halves whole and keep ratios the same? Double everything. So 1 doubled is 2. 3.5 doubled is 7. 4 doubled is 4. And 3 doubled is 6. So in order to get my 1 to 3.5 to 2 to 3 ratio, I'm going to turn that into 2 to 7 to 4 to 6. So this is how you can make it a little bit less trial and error. carbon first, then hydrogen, then oxygen. And if you come back here to cut that oxygen in half and get a half answer, then just double everything. So it's going to give us our compounds and our coefficients. Okay. Now we've covered 5 different types of equations. You've got to be able to predict your formulas. You've got to be able to predict your products. You've got to be able to balance the equation. Just keep your subscripts down first and don't change them when you go back to balance the equation. So I hope these tips help you figure out your equations. The next thing that we're going to be looking at is a special type of equation. So in notes B, we're going to look at something called a net ionic equation. I'll see you there.